Hey folks, welcome back to Combo Class. I'm your teacher Demotro, and I've been researching some weird ways that numbers could be counted. Now, normally in a positional numerical base like our base 10 system, where each spot in a number represents how many of some given power of that base number you have, the base number is some positive integer. And we've explored negative integers too. But what if you counted in a base that wasn't an integer, like base 3/2, or base square root of 2, or base pi? Believe it or not, you can design a numerical base around a fractional base number, or a square root or cube root for your base number, or other irrational numbers like the golden ratio or e or pi. And surprisingly, most of these bases are even good at representing whole numbers. So let's jump into some crazy bases. Now we're gonna start with base pi, because that's the one a bunch of people requested. But I gotta admit, base pi isn't gonna work as cleanly as some of the later ones we'll encounter. In base pi, each spot represents how many of a power of pi you have. And since there's a pi to the 0th spot, there is a ones place. But without using a million different characters of digits you could put in the ones place, can we represent other integers in base pi? Well, base pi could come in handy with things like talking about how much more a circle's circumference is to its diameter, or comparing different circles' areas to their diameter, but it's not going to be able to represent integers. The only way to represent an integer in base pi would either be to have a character that big for your pi to the 0th spot, which is your ones place, or to have an infinite amount of digits after the decimal. Kind of like how in our base 10, pi takes an infinite amount of digits after the decimal to try and represent. In base pi, an integer like 10 would take an infinite amount of decimals to try and represent. So unfortunately, base pi isn't going to work very smoothly for representing whole numbers, and neither is base e or other transcendental numbers for our base. It's going to work a lot better when our base is an algebraic number, meaning some sort of either fraction or a square or cube root based thing that is the solution to some algebraic equation. So what about a fractional base, like base 1/2? There, each spot in a number would represent how many of a given power of 1/2 you have. And if we look at what that breaks down to, the 1/2 to the 0th place still is a ones place. And then if we go the direction that we typically consider numbers to be growing larger as you add digits, the places actually get smaller. This is how many 1/2s you have, the 1/4 place, the 1/8 place, and so on. But if we look beyond the decimal, where in a positional numerical base, we get negative powers of the base number. 1/2 to the negative first power is 2, 1/2 to the negative second power is 4, and we get the powers of 2 going upward. It's sort of like the numbers we could make in binary or base 2, but flipped, meaning that we could still use the characters that binary uses, 0 and 1, and represent things in this base. So let's look at a little chart of how our base 10 numbers would be written in base 2, binary, and base 1/2. A number like 2 is written 1-0 in binary, or 0.1 in base 1/2. A number like 6 is written 110 in base 2, or 0.11 in base 1/2. It looks like they're mirrors of each other, but with a decimal stuck one place in. And it's true, the base 1/2 representations of integers will just be a flipped version of how base 2 binary writes them, but with a decimal point stuck right in there after the first place. Now, you know how I like hyper 11s, my nickname for numbers composed of just the digit 1 in some base? Well, the hyper 11s in base 1/2 are pretty interesting, meaning the numbers that base 1/2 writes with only the digit 1 and presumably only in front of the decimal point, nothing after a decimal point. Well, the number that base 1/2 writes as 1, 1 translates back into our base as they add 1 of the 1's place and 1 of the 1/2's place, which adds up to 1.5. And if we see a number that base 1/2 would write as 1, 1, 1, that's 1 of the 1's place, the 1/2's place, and the 1/4's place, adding up to 1.75. And if we saw a number that base 1/2 wrote as a hyper 11 with a billion ones in it, that would be equal to the number that we know as very close to 2. And the more ones we stacked, the closer we'd get to 2. But we'd never pass it because it's sort of like with each one we stack, we're jumping halfway between 0 and 2. And if you jump halfway at each point, you'll never pass the end. And since the limit of this geometric series, if you were able to add up the infinite amount of terms, approaches 2, it's sort of like an infinite hyper 11, meaning a hyper 11 composed of an infinite amount of ones, if you could somehow do that, in base 1/2 would be equal, and I'm writing base 1/2 just to clarify what base we're talking about, would be equal to the number we know as 2. Technically, we would say that the limit of adding ones approaches 2, but it's kind of fun to think of it as the infinite hyper 11 equals 2. Now, what about a base that's a fraction greater than 1, like base 3/2? Now, in that base, we're going to need to use a character for the digits 0, 1, and 2, the number 1 less than 3, because we do have a 3 hanging out up there in the numerator of that fraction. But with these digit symbols, we're going to be able to do a surprising amount. Now, if we look at the places in a base 3/2 number, not including any fractional part, we get a 1's place from our 3/2 to the 0, and we get a 3/2 place there, and then they start looking like weirder and weirder fractions. 9/4 is there, that's how many 27/8 there are. Yet with the digits 0, 1, and 2, we can build integers. Here's a chart of some numbers as we know them in base 10, then how base 3/2 would write those numbers. And the first two numbers are pretty obvious to figure out because we have up to 2 of that 1's place to use. But to make 3, if I don't want to use a character for the number 3, I have to move on to this place and use 2 of the 3/2 place and none of the 1's place. And 2 times 3/2 does get us 3. And if I want to make something larger, it starts to get a little trickier. Like to make 6, I need to write 210 to mean 2 of the 9/4 place, 1 of the 3/2 place, and none of the 1's place. And it's true that 2 times 9/4 plus 1 times 3/2 adds up to 6. But what if I wanted to translate a bigger number? Is there some pattern as to how I would write it? Well, there's actually a fun game we can use to figure that out. To translate an integer into base 3/2, I can take that amount of some item, like here I have 10 dice, and play a game where I put them in the first box of several compartments I create. Then I'm going to take 3 at a time whenever possible, throw 1 out, and move 2 to the next box. Like there's another 3, I'll toss 1 and move 2, another 3, I'll toss 1 and move 2, and I'll do that until there isn't enough for another group of 3 to do that with. Like there's 1 left there, so I'll just leave that. Now I'm going to continue doing the same thing in this box where I take 3, toss 1 and move 2, take 3, toss 1 and move 2, and now there's none left there in this case, so we'll move onward. Repeat where we find 3 when possible, toss 1 and move 2, and at this stage there's no more 3's to do that with, so I'll end and write down how many are in each of these boxes. 2, 1, none, 1, And it turns out that number, 2101, is how base 3/2 writes 10 of a thing. And if you want your own challenge, try and figure out how you could come up with a variation on that to figure out integers in other fractional bases, like maybe base 4/3. So those were some fractional bases, but could we make integers using an irrational number for our base, like base square root of 2? Now that's obviously not an integer, but if we look at each spot in the number that would represent powers of the square root of 2, all of the spots with an even number exponent sort of wipe out the square root. Like square root of 2 squared is 2, square root of 2 to the 4th power is 4, and so on. Meaning we do have the same tools in our toolkit that we would have using binary, plus these extra tools that we wouldn't want when making an integer. So using symbols for the digits 0 and 1 like binary did, we can sort of make a number using a stretched out version of how binary would write it. Like the number 3 written in binary is 1, 1. And the number written in base root 2 just sticks a 0 in between those because we don't want any of the root 2's place. Or the number 7 written in binary is 1, 1, 1, and base root 2 sticks a 0 between each of those. Similar to something we saw with base -2 in an earlier episode, when we're writing integers in base square root of 2, we don't notice any of them with an even number of digits in its representation. These all have 1, 3, or 5 digits, and eventually we would start hitting 7 and 9 digits. That's because if we had an even number of digits, it would have to be including one of these square rooty ones, which is actually pretty awesome because it means that base square root of 2 can represent all of the integers. Plus, if we had written something like 1, 1, that would translate back into our base as 1 plus root 2. So we can write these other irrational combos just writing strings like 1, 1. We have the integers and some extra stuff right at our disposal. And we could make numerical bases out of other square roots too. Like what about base root 10? Now we're gonna need to use the digits between 0 and 1 under whatever's inside the square root. And then we're gonna be able to kind of copy base 10 with zeros in between it, like how we were copying binary with zeros in between before. Like if I want to write the number 123 in base root 10, I just need 1 there, none of those, 2 there, none of those, and 3 there. And once again, I'd be able to write all of the integers in this base, plus some other things that involved root 10s. We can even make a base out of a cube root number, like base cube root of 10, and we'd still use the digits between 0 and 1 under the number inside the root. And to express integers in base cube root of 10, that would look similar to integers expressed in base 10, but we would only want the non-zero digits on the spots with a 3-even numbered exponent to cancel out the cube root. So to write 123 of a thing in base cube root of 10, we would write 1002003 and have 2 zeros in between each of the digits. Now, one of my favorite irrational bases is the golden ratio base, or base phi, this Greek letter it's commonly written with, and the golden ratio is 1 plus the square root of 5 all over 2, or approximately 1.618, and then an infinite non-repeating decimal, because it is an irrational number. And although it is an algebraic irrational number that's going to be possible maybe to write integers with, as opposed to a transcendental base like pi, it's going to be a lot more difficult than base square root of 2 or something, because apart from the 0th power spot, none of these other places are going to be an integer on their own. To make an integer, we're somehow going to have to combine different powers of the golden ratio. But somehow, using just the digits 0 and 1, we're going to be able to combine distinct powers of the golden ratio to make any integer. To figure out how to do that, let's bust out an important identity about the golden ratio, which is that it's equal to 1 plus its reciprocal. Reciprocal meaning 1 divided by itself. And I wrote that identity twice because it's going to come in handy to have a pair of them. Over on this one, we're going to subtract 1 from each side, and we're given the golden ratio minus 1 equals 1 over the golden ratio. And over here, we're going to subtract 1 over the golden ratio from each side, giving us the golden ratio minus 1 over the golden ratio equals 1. And then we're going to divide each side of this by the golden ratio, giving us 1 minus 1 over the golden ratio squared equals 1 over the golden ratio. Now, both of these ended up having an equals the golden ratio, so we know that that also equals that. We can substitute them together to say golden ratio minus 1 was equal to 1 minus 1 over the golden ratio squared. And now we can shuffle over our terms, add that to each side, and add the 1 to each side, and we're left with the golden ratio plus 1 over the golden ratio squared equals 2. And we can rewrite this in terms of powers of the golden ratio because that's the golden ratio to the first power, and something's reciprocal is normally it to the negative first power, and this mega reciprocal thing where we have 1 over it squared is the same as it to the negative second power, so we can add that in and write the golden ratio to the negative second power for what that was. And now we have a way to make the number 2 using distinct powers of the golden ratio. Meaning if we wanted to write the number 2 in the golden ratio base, I can put a 1 on the spot that has golden ratio to the first power, a 0 on the ones that we didn't use, and a 1 on the spot that had golden ratio to the negative second power. So it would be written as 10.01. That's how the golden ratio base writes the number 2. Now, if I wanted to write the number 3 in a golden ratio base, I could think about just adding 1 onto the golden ratio to the 0 powers spot, because that's a 1 spot, and think about writing 3 as 11.01. But something interesting is that when we multiply this identity by the golden ratio on each side, we see another identity. The golden ratio squared equals the golden ratio plus 1. And remember, this can now be written as powers of the golden ratio because 1 is the golden ratio to the 0th power. And we get this new identity that the second powers spot is equal to 1 in each of the first powers and 0th powers spot, meaning that 1, 1 there is the same as a 1 there and 0s there. So 1, 1 in the golden ratio base is the same as 1, 0, 0. And it turns out that whenever we see a 1, 1 in a golden ratio base representation, we can transform it into a 100-like thing and not need any 11s in the more proper form of expressing integers in the golden ratio base. So in the proper way of writing integers here, it's the opposite of me talking about hyper 11s and numbers filled with 1s. You never even get an 11 in a row. No 2 1s in a row are necessary. And so the more standardized form of writing 3 here is 100, or what looks like that, 0.01. Now, before anyone gets annoyed that the golden ratio base has multiple ways of writing some numbers, remember that that's true in our base also. In base 10, something like point infinite nines is the same as the number 1. So you're gonna have to get used to some numbers having multiple ways to write them. And by adding up distinct powers of the golden ratio, you can create any integer. Like, it turns out the number 5 is exactly equal to the golden ratio cubed plus the golden ratio to the negative first power plus the golden ratio to the negative fourth power, which means if we want to write 5 in the golden ratio's base, we put 1s on those spots and 0s on the other spots, giving us 1000.1001 as the way they write 5. And you'll notice that there are no 2 1s in a row anywhere here. Nothing that looks like an 11. And that's because, like I mentioned, all the 11s can be turned into 100-looking things, which is considered the more standard or proper representation of them. And there are plenty of other possibilities for what fractional or irrational bases could be, and those might sneak into future video topics, although I know next time that we talk about number bases, the main subject is going to be base 2i and other imaginary bases. And if anyone wants to play around with how to make integers in base 2i in the meantime, note that you will need characters for 4 different digits, like having a character for 0 through 3. All right, and one last announcement I need to make is that I've gotten some requests to make a Patreon, and I have made one now. So if you want to get some cool rewards like bonus videos or chances to talk to me more directly, or just want to support grade -2 being even cooler than grade -1 is, well, check that out. There's more info in the description. Thanks so much, and I'll catch you guys next episode.